Okay, the camera died, so this is already written, but I'll talk through it. For number 20, it says the gravitational field strength is 2g, and I have half the mass, and I want to know what happened to the radius. And it's like blank radius squared with 1/2 on top would give me 2. So you could do like guess and check kind of and plug in what 1/2 squared would be. Or sorry, 1/4 squared, so that would be 1/2 over 1/4, but it gets squared, which is 0.5 over 1/16, which definitely does not give me 2, so A we crossed off. Try the next one. You have 1/2 over 1/2 squared, that would give me 1/2 over 1/4. 0.5 over 0.25 does give me a factor of 2g, which is what I want, so it was B. Number 21, so we wanted the expression for orbital velocity of a satellite orbiting a planet. So I want to know what the velocity would be using just like the mass, etc. And obviously the radius, you would need to know the radius of the circle, r. So if it's moving in a circle, that tells us probably going to use centripetal force. Now the centripetal force is provided by the gravitational force, right? It feels this force towards the center or towards this mass because it's the gravitational force. So I'm going to say that Fc equals Fg. Fc is mv squared over r. Now your force of gravity, a lot of you are tempted to do m little g. That only works if you know little g. We know little g on Earth is -9.8, just use 10. But for a random satellite orbiting a random planet at some radius that we don't know, we can't just use little g because we don't know little g. So let's use the force of gravity, big G, m1, m2 over r squared, and you'll see that the little m's cancel. One of the r's cancels, and then you just take the square root, so it's square root of gm over r, m being the mass of the planet or the thing you are orbiting around. Both blocks slide from rest on each ramp. The ramps are the exact same height, and they have the same coefficient of friction. When each block reaches the bottom, how does the change in potential and change in kinetic compare for each ramp? So think about change in potential energy is just the change is mg delta y, or the height. They have the same mass and they have the same height, so they should have the same change in potential energy. Now change in kinetic, well, it starts from rest and then the velocity at the end. Now most of you are probably thinking like, oh, it would have the same change in kinetic because it says the same potential energy. But energy is not conserved here because it says that they have friction. So both of these are going to lose some of their potential energy due to friction. Now you'll notice that they will not lose the same amount of friction because ramp 1 has less distance to travel than ramp 2. And we know that the work due to friction is, any work is force times distance. So assuming they had the same friction force, which they actually don't, it's a different angle, but we don't need that. If this one has a greater distance, then it's going to have more work done, so this one loses more energy. And this one does not lose as much energy. So the greater change in kinetic energy is going to come from ramp 1 because it doesn't lose as much. Its change in kinetic is closer to the change in potential, whereas this one is change in potential minus a lot more work due to friction. So it doesn't have as much kinetic energy at the end. So it has less change in kinetic, whereas this one has more. And which one reaches the bottom first? So ramp 1 for 2 reasons. First reason being, even if it was frictionless, this one would reach the bottom first because it's steeper, so it has a greater acceleration, and also it loses less of its energy due to friction, so it'll go faster for another reason. Number 23, so we have a graph of the force and the displacement, and as it goes from the 0 to the 1 meter, it gains a speed of 2. And I meant to say that it starts from rest, so it starts from rest, and this is like my final velocity is 2. And we have the force and the displacement. So if we're looking for the mass and we have velocity, well, that's thinking about like 1/2 mv squared or kinetic energy. And how we can relate kinetic energy to force and displacement is work, because work is equal to force times the distance, and work is also equal to the change in energy. So what is tempting, tempting to do here is to just say like, oh, 20 times 0.1 gives me my force, or gives me my work. But that is not a constant force, right? Your force was 5 here, and then 10 or something close, blah, 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 up to 20. So we need to just do the area under the curve because that's going to take into account that this was a changing force. So then this is a triangle, so base of 0.1, height of 20 divided by 2 gives me that work was 1 joule. Yeah. And then that work is also equal to the change in kinetic energy. Man, I have that wrong in my answer. Okay. Work is equal to the change in kinetic energy in this case. It's gaining speed, doesn't say anything about gaining height. So then this is 1. Change in kinetic would be 1/2 v squared minus 1/2 mv squared. But then it started from rest. This is just 0. And the velocity at the end was 2. So 1/2 mass 2 squared equals 1. That would be 1/2 of 4. So 2m. So then your mass is just 0.5 kilograms. Number 24, Tarzan of mass m runs at a velocity v towards a vine of length L. Determine the maximum height. So we're starting with kinetic energy, and potential would be 0 on the ground. When he goes up the maximum height, well, he'll stop moving at the maximum height, so he'll have all potential energy. So his kinetic energy would just be 1/2 mv squared. And if he goes all the way up to the top, his kinetic is 0, so his potential is just the energy he started with. So his potential, or you can think about it as the 1/2 mv squared goes into mgh. So those are equal to each other, because we're going to assume that there was no friction loss. Masses cancel. The maximum height would be v squared over 2g when you divide the g over. So you'll notice that this height depends on the velocity and gravity. It does not depend on mass. Not depend on mass. And it does not depend on the length of the vine. So if you're like, wait, what is that? Was just extra information. It doesn't matter how long it is. At some point it'll matter, right? If your height is greater. Actually, no, it won't matter because it'll continue. So how long the string is doesn't matter. If this had been a really, really long string, if he came in at the same speed, he would still go equally. Oh, you can see. He would still go equally as high.